And so for imidazole, once again, we have the same sort of situation that we had for pyrrole with this nitrogen right here. So at first, it looks like that nitrogen might be sp3 hybridized, but we can draw a resonance structure for it. So we can take these electrons in here and move them in here, which will kick these electrons off onto that top nitrogen. So let's go ahead and draw the resonance structure for that. So we would have some pi electrons here, we would have a double bond here, we would now have a +1 formal charge on this nitrogen, and we would have a -1 formal charge on this top nitrogen right here, like that. So once again, we've seen that this nitrogen in blue, it's actually sp2 hybridized, right? So let me go ahead and highlight it in blue over here on the right. This nitrogen is actually sp2 hybridized, so it's the exact same situation that we saw in pyrrole, which at first it looks like those electrons might be localized to that nitrogen. Those electrons are actually not. Those electrons are delocalized in the ring because of the possible resonance structure. And so we've determined that that nitrogen in blue that's bonded to that hydrogen is sp2 hybridized. So over here, I can go ahead and identify that nitrogen in blue that's bonded to the hydrogen. It's sp2 hybridized, therefore it has a p orbital like that. So I can go ahead and draw the p orbital on that nitrogen. If I look at the carbons, in this molecule, right, so I'm going to go ahead and highlight these carbons in red here. So these 3 carbons of my original dot structure, we can see they have a double bond to them, so those are all sp2 hybridized. So I can go ahead and draw in the p orbital on those carbons as well. And then once again, going back to the original dot structure, and this time looking at the nitrogen, so I'm going to go ahead and draw this one in magenta. So this nitrogen right here, if I look at this first dot structure, it's just like the example in pyridine that we saw in the last video, right? So it's actually sp2 hybridized, and since it's sp2 hybridized, we could think about these electrons in here in magenta as participating in resonance, and the electrons in blue here as being localized to that nitrogen atom, localized to an sp2 hybridized orbital. And so I can go ahead and identify this nitrogen in magenta over here. So I'm saying this nitrogen is in magenta. I can say that it is sp2 hybridized. It's the same situation as pyridine. So I can go ahead and draw a p orbital on it. And that lone pair of electrons in blue that's on that nitrogen, that lone pair of electrons occupies, I'm going to go ahead and put them in blue, that lone pair of electrons is going to occupy an sp2 hybridized orbital on that nitrogen. So those electrons are not involved in resonance. Those electrons are localized to that nitrogen. And so when we go ahead and think about the criteria for aromaticity, right, our first criteria are, all right, we have overlapping p orbitals here, and so I can see that that is the case, right? We have overlapping p orbitals. Everything is sp2 hybridized in our ring, and of course we also need 4n plus 2 pi electrons. And so let me go ahead and label those in magenta. So my pi electrons, right, going back to my original dot structure, here's 2, right? Here's 4, and then this lone pair on our nitrogen, right? Those are actually pi electrons. When we think about this resonance structure here, so I'm going to go ahead and label them in magenta again. So there actually are 6 pi electrons in the imidazole molecule, and those pi electrons are delocalized around this ring, around these overlapping p orbitals, and so the imidazole molecule is aromatic as well. So the imidazole molecule is actually extremely important in biochemistry. So let's take a look at a famous molecule that contains the imidazole ring, and this molecule is called histamine, which anyone who has allergies has heard of histamine. And you can see the imidazole ring over here on the left on the histamine molecule. So if you want to understand biochemistry, it's very useful to understand these concepts found in organic chemistry. And so histamine would be an example of a biological aromatic heterocycle. This portion of the molecule, the imidazole ring, is aromatic. It satisfies the 2 criteria as we have seen. So let's do one more example of an aromatic heterocycle here. This time let's look at an example that has sulfur in it. So this molecule is called thiophene. And this this is really the sulfur analog to the pyrrole molecule that we studied. So let's start by analyzing this sulfur in terms of its steric number, right? So I'm going to look at this sulfur right here. We're going to calculate the steric number of that sulfur. So number of sigma bonds to that atom. So here's a sigma bond, and here's a sigma bond. So we have steric number is equal to number of sigma bonds plus number of lone pairs of electrons. So we have 2 lone pairs of electrons around that sulfur like that. So So that would be 2 plus 2, which is equal to 4, which implies that sulfur is sp3 hybridized. But that doesn't work for our concept of aromaticity, because in order for something to be aromatic, our atom needs to be sp2 hybridized, so it has a free p orbital, just like these carbons right here. So once again, these carbons all have a double bond to them, so those carbons all have a p orbital, so I can go ahead and sketch in those p orbitals on those carbons like that. So the sulfur looks like it's sp3 hybridized, but of course it's going to be a similar example to the pyrrole molecule. I can show a resonance structure for this thiophene molecule. I can take one of these lone pairs of electrons, I'm going to say it's the lone pair on the right here, and I could show them moving in to form a pi bond between the sulfur and this carbon, which would of course kick these electrons off onto that carbon. And so when I go ahead and draw this resonance structure, right, so now there's a pi bond between the sulfur and this carbon. Lone pair of electrons moved out onto this carbon, giving that carbon a -1 formal charge. There was still a lone pair of electrons, still a pi bond, I should say, over here, and there was still a lone pair of electrons left on this sulfur. So now we can also give this sulfur a +1 formal charge, and we can analyze it in terms of its steric number. So once again, number of sigma bonds. So this is a sigma bond, this is a sigma bond, and so the steric number would be equal to 2 plus how many lone pairs of electrons? Now there's only 1, so 2 plus 1 is equal to 3. So now we can see that it's actually sp2 hybridized, so it has 3 sp2 hybrid orbitals, and one of those sp2 hybrid orbitals is going to contain that lone pair of electrons in blue there. So that lone pair of electrons, and again, it's sp2 hybridized, which means it has 2 other sp2 hybrid orbitals, and those hybrid orbitals are forming bonds with those carbons there. Since it's sp2 hybridized, it also has an unhybridized p orbital, so I can go ahead and draw in that unhybridized p orbital. And so I could think about one of those lone pairs of electrons on my original dot structure occupying a p orbital. So let's go back here and look at the thiophene original dot structure I drew. I could think about one of these lone pair of electrons. I'm going to mark it in magenta as occupying a p orbital.